Hello, kiddos, and welcome to the beginning of Chapter 16. For 16.1, we're just going to take a look at water ionization and acid-base strength, and we're going to recap a little bit of our Chemistry 20. All right, so we're going to take a look at what is going on when water self-ionizes into hydronium ions and hydroxide ions. And the fact that that happens is going to lead chemists, or did lead chemists, to think about water ionization and a formula that goes with that and all kinds of fun stuff. All right, let's just get started, kiddos. So over the years, scientists using very sensitive instruments have found that pure water is slightly conductive, which we knew about this in Chem 20. One scientist by the name of Savant Arrhenius theorized that the conductivity was due to the presence of ions in the water. So where did those ions come from, and why were they so low? Arrhenius explains that pure water is made up of both our hydrogen ions or hydronium ions. Later, we learned that they were actually hydronium ions and hydroxide ions, and water molecules together in an equilibrium state. He also theorized that the amount of these ions is so small that the equilibrium favors the water molecule, the left side. We use the following equation to represent his theory. So we kind of looked at this and said, okay, I have water, and why is there two waters here? Because if I were to balance, it's actually 2H2O, liquid, right, kiddos? So there's a very small probability, right, very, very small probability that it's going to ionize into hydronium ions and hydroxide ions. Typically, it favors this side where it stays as the water. That's why pure water, with the instruments that we have, shows up as neutral, where in real life, it does conduct electricity, and it doesn't conduct electricity, pure water, because our instruments aren't very sensitive. But if we use very, very sensitive instruments, we would see that there is a little bit of conductivity due to the fact that a very small percentage, right, ionizes into H3O, the hydronium ion and the hydroxide ion. So we came to, if we use this idea, we can come up with a Kc value. So we have our hydronium ions over hydroxide ions. We don't include water in this case because it's a liquid, okay? So we have Kc is equal to H3O plus aqueous and hydroxide ion aqueous. All right, so let's take a look here. Our Kw, so our Kw then is equal to the concentration of hydronium ions multiplied by the concentration of hydroxide ions, should give you 1.0 times 10 to the negative 14 at SATP. Remember, SATP is standard ambient temperature and pressure, and it's at around 25 degrees, but that's kind of arbitrary. Kw is the ionization constant for water. So that's really important. This actually is like a shortcut from what we did in Chem 20 when we're looking at pH, pOH, concentration of hydroxide ions, and concentration of hydronium ions. So this is like a really cute shortcut. So in a neutral solution, we would say that the hydronium ions is equal to the hydroxide ions, which makes sense, right, kiddos? Which means that basically each of these, the hydronium ion and the hydroxide ion, are each, if in a neutral situation, 1.0 times 10 to the negative 7 moles per liter. Okay, so neutral solutions, let's take a look here. The hydronium ion is equal to 1 times 10 to the negative 7. And remember, we use this to come up with this pH of 7, right, kiddos? That's where that comes from. It's the concentration, right? There's 1 times 10 to the negative 7 moles per liter concentration of the hydronium ion in a neutral solution. An acidic solution, however, is going to, if you think about it, in an acid, you have more hydronium ions than if you're comparing that to a neutral substance, right? And in a basic solution, you have actually less hydronium ions than if you're comparing that to a neutral solution. So there are higher concentrations of hydronium ions in acidic solutions. There are lower concentrations when you compare it to a neutral solution. And in comparison, there's a lot lower amounts of hydronium ion concentrations in a base. In fact, in a base, you're going to have a lot of hydroxide ion concentrations and low hydronium ion concentrations. In an acid, you have high hydronium ion concentrations and very low hydroxide ion concentrations. Kind of tongue twistery. So we have a very kind of quick way of finding hydronium ions and hydroxide ions. Okay, it's just a very quick formula. It's your your water constant over your hydroxide ions, and the opposite. You have your to find the hydroxide ions. You do the concentration of the hydroxide ions. You think about oppositely. So let's take a look at an example. A 0.15 mole per liter solution of hydrochloric acid at 25 degrees Celsius at SATP is found to have a hydronium ion concentration of 0.15 moles per liter. Calculate the amount concentration of hydroxide ions. Okay, cool. How do we do that? This is what we're looking at. We're looking at the fact that according to the modified Arrhenius theory, your HCl reacts with water, right? So that this hydrogen is leaving, bringing with it your hydrogen ion has a positive charge. That's where we get the H3O plus. If that hydrogen leaves, obviously you're left with a chloride ion. You also know that this is a spectator ion. So it basically just like ionizes, right? It ionizes, doesn't dissociate, acids ionize, and it basically dissolves in the water. No big deal. So we are looking for the concentration of the hydroxide ion. So it's our Kw over our H3O plus ion concentration that's given to you right here. So we just use our 1.0 times 10 to the negative 14 over that, and we get our answer, right? Using Kw relationship, the hydronium ion concentration is 6.7 times 10 to the negative 14. Okay, so here's another question. Calculate the amount concentration of a hydronium ion, okay, in a hydronium ion in a 0.25 moles per liter solution of barium hydroxide. Now, here we want the hydronium ion concentration. This time they don't give you an acid. That would be easy, finding the hydronium ion concentration in an acid. Now they give you a base, barium hydroxide. So in Chem 20, take a look at what we had to do in Chem 20. We had to find the hydroxide ion concentration using negative log, remember, to find the pOH, then subtract 14 from the pOH to find the pH, then finally use a 10 to the negative pH to find the hydronium ion concentration. But now we have this really, really easy way of finding it. No big deal. We don't have to go through 3 steps. But let's take a look first. First thing you're going to do, you're going to take a look at the barium hydroxide, and you're going to dissociate. Barium, there's one, it's going to dissociate into one barium ion with a + 2 charge. Take a look over here, we have a subscript of 2, right, for the hydroxide ion concentration, and that becomes a coefficient. So it's a 2 to 1 to 1 ratio, right? So if the concentration of the ion, right, is, it says here, calculate the amount of concentration of hydronium ion in a 0.25 moles per liter solution. So we know that the solution itself, right, has a concentration of 0.25 moles per liter. And we know that for every one of these, there's 2 of these. So I have to take the 0.25 moles per liter and multiply it by 2. And you get 0.50 moles per liter of the hydroxide, right? Because it's double, it's twice as concentrated as the barium hydroxide solution because it's a 1 to 1 to 2 ratio. Now that we have the concentration of the hydroxide ion, we can use this lovely little formula, H3O plus, to find the concentration of the hydronium ion, your Kw over your concentration of your hydroxide ion. Not the barium hydroxide, just the hydroxide. Put in your numbers, kiddos, and you get an answer. This is way easier than that. Because even if we did the Chem 20, you'd still have to do this part first. I know, good times, right? So here's another one. Keep in mind you have the formula to find the concentration of the hydronium ion and the concentration of the hydroxide ion. You know how to do that. It's just Kw over the thing you're not looking for, I guess. Determine the hydronium ion and the hydroxide ion amount concentrations in 500 milliliters of an aqueous solution for home soap making containing 2.6 grams of dissolved sodium hydroxide. Okay, I actually made soap at home. It's actually pretty fun. But anyways, I digress. I'm going to use my 2.6 grams plus my molar mass of the sodium hydroxide in order to convert grams to moles. Now that I have my moles of sodium hydroxide, I'm going to divide that by my volume because it's just like C is equal to N over V to find the concentration, number of moles over volume. My volume is 500 milliliters, but I have to change it to liters, right? 0.500 liters. It has to be in liters because my concentration is moles per liter, and I get 0.13 moles per liter. Now, if I take sodium hydroxide, this is different from the previous example, because with sodium hydroxide, if I dissociate that, it's a 1:1:1 ratio. So if this is my concentration of sodium hydroxide, my hydroxide ion concentration is going to be exactly the same, okay? Because it's a 1:1 ratio, so that stays the same. To find the hydronium ion concentration, it's just my Kw over my concentration of a hydroxide ion, and I will get 7.7 times 10 to the negative 14. That is equal to my hydronium ion concentration. And concentration, instead of writing it, you can use these square brackets. And this is my hydroxide ion concentration. Okay, cool. Let's move on to another example. Calculate the amount concentration, and anytime you see amount concentration, it's just moles per liter, of the hydronium ions. So we want to find the hydronium ions in a 0.100 moles per liter aqueous solution of ammonia. So in this case, we're talking about ammonia that is used in a spray bottle for window cleaning solution. A reference states that there is a 2.1% reaction of the dissolved ammonia with water. So what that means is this only happens, this reaction only happens 2.1% of the time. So it's actually quite low. This is a weak base, kiddos. So this is going to react with water according to Renus's modified theory. This time the hydrogen is going to react in this direction, right? Bringing with it an H+. Does that make sense? And that's where this 4 comes from and where the plus comes from. The positive charge comes from the extra hydrogen ion that is leaving the water and reacting with the ammonium or the ammonia to make the ammonium ion plus your OH negative. Does that make sense? The only thing you have to be aware of is this does not happen 100% of the time. It only happens 2.1% of the time, which is really quite low. So I have to take my 0.100, right, and multiply it by 2.1. Now, percent. Now, you have to understand that 2.1% mathematically does not equal 2.1, because 2.1 means double, and it's not double, it's only 2.1%. So this is where this 100 comes from. That's going to convert my percent to a decimal. That's a decimal. And we need to multiply it by a decimal, the decimal version of what 2.1% is, to get us our new concentration, moles per liter, because it's 0.0021. You have to use this, kiddos. This is false. This is making the assumption, if you use this value, it's making the assumption that this is 100%. And it's not, because it's that double arrow. It's only 2.1%. Okay, now that we have our concentration of our hydroxide ion, now we can find the concentration of our hydronium ion by just going Kw over the hydroxide ion. Here's my 1.0 times 10 to the negative 14 over my 0.0021 moles per liter, which is going to give us 4.8 times 10 to the negative 12 moles per liter. That's a very, very small amount of hydronium ions, which makes total sense because this is a weak base, okay? So this would be a pH of about 12, okay? And a strong base would be like a 13 or a 14. Okay, so that makes sense. Using Kw relationship in 0.100 moles per liter aqueous ammonia, the hydronium ion concentration is 4.8 times 10 to the negative 12. Keep in mind, though, that a strong base, right, a strong base compared to ammonia would be something like sodium hydroxide. Remember from Chem 20, all strong bases have the actual hydroxide ion in the chemical formula. Okay, we're almost done, kiddos. This reminds me of Chem 20, so this is like flashback. Communicating concentrations, pH and pOH. You know that if you're finding the pH of a solution, it's the negative log. You just apply negative log of your hydronium ion concentration. And that only works with acids, okay? So if you want to find the pH of an acid, you just take the negative log of the hydronium ion concentration. To find the hydronium ion concentration of an acid, you take 10 to the power of your negative pH. If you're looking for the pOH, it's your negative log of your hydroxide concentration. And to take the concentration of the hydroxide ions really quickly, it's just 10 to the power of your negative pOH. If you have your pOH, you just go 10 to the power of negative pOH to get you your hydroxide ion concentrations. Also, be very aware that pOH plus pH is equal to 14. So if I had a pOH of, let's say, 10, right away you can find the pH, just go 14 subtract 10 is equal to 4. So that kind of thing. So this is very Chem 20, but that's it. Now it's a little different. So let's talk about what a strong acid means compared to a weak acid. A strong acid explained as an acid that reacts quantitatively. Remember, quantitatively is like, oh, look, I can use stoic. I don't have to use ice tables or that kind of thing with water to form hydronium ions. What that means is that hydrochloric acid being a strong acid, it's going to react with water. Notice this, it's only one arrow. It's not a double arrow. It means that it's going to favor the products pretty much always more than 99% of the time. So it's totally different than a weak acid. With a weak acid, you use your ice tables to figure out concentration and that kind of thing. With a strong acid, because there's only one direction of the arrow, which means that this is going to occur more than 99% of the time. And that's only because we're looking at the purity of your substances, and we can't with all confidence say that we're dealing with 100% pure stuff, okay? So a weak acid, however, is explained as an acid that reacts partially with water to form hydronium ions, and it's usually less than 50% of the time. If you look at acetic acid, okay, it's going to react with water to form your hydronium ion only 1.3% of the time, as opposed to more than 99%. So in this case here, we don't get a lot of hydronium ions. It's a weak acid, okay, because we don't have a lot of these guys. Hydrochloric acid is the strong acid because we have a lot of these guys. And it's the presence of the hydronium ions that give an acid its acidic properties. Okay, percent ionization, it's a way to express acid strength quantitatively. So if we're talking about an acid, this is just a formula for an acid, right, which is just basically hydrogen plus something else plus water, is going to give you your hydronium ion plus your negative anion, or an anion is negative anyways, that was kind of silly. So your percent ionization is equal to your hydronium ion over your the concentration of your acid times 100%. Why am I timesing 100%? Because this is percent ionization. Anytime you want to find the percent of something, you always have to times it by 100. It relates the concentration of the hydronium ion at equilibrium to the original concentration of the acid. So here's an example. In a 0.10 moles per liter solution of acetic acid, only 1.3% of the CH3COOH molecules have reacted at equilibrium, that's acetic acid by the way, to form hydronium ions. Calculate the hydronium ion amount concentration. So now we know that it's only 1.3%, right? But you cannot mathematically think that 1.3% mathematically is 1.3. The percent tells you that it's a lower number. You have to divide that number by 100, or if you want, do that really quick, and you just multiply the concentration by the decimal rendition of the 1.3%, which is going to give you 1.3 times 10 to the negative 3 moles per liter. If you want to include that in your calculations right on, 1.3 divided by 100 times 0.100 moles per liter, or just go 0.013 times 0.10 moles per liter. Just don't forget to convert the percent to a decimal. So yay, another formula. Remember, percent ionization, right, is equal to hydronium ion over the concentration of the acid. And you can rearrange the equation to solve for equilibrium hydronium ion concentration. So you can rearrange the formula to find the hydronium ion concentration. And you can also rearrange the formula to find the concentration of the acid, or in this case, the initial concentration of the weak acid. This is for the initial concentration of the weak acid, provided obviously that you have the percent ionization. All right, so here's an example. The pH of a 0.10 moles per liter methanoic acid solution is 2.38, so that's our pH. Calculate the percent reaction for the ionization of methanoic acid. Right on. The first thing you're going to do is you're going to change this number to the concentration of your H3O. And you do that by just simply going 10 to the negative pH. So 10 to the negative 2.38 moles per liter is going to give you 4.2 times 10 to the negative 3 moles per liter. I'm going to rearrange the formula to look for my hydronium ion concentration. So it's basically the percent ionization over your acid concentration. And here is your acid concentration, right? And this time, I am looking for percent ionization concentration, which is going to be 4.2%. Once I rearrange it and I find my percent ionization. Okay, that's it, kiddos. Enjoy your day, and I will talk to you later. Bye-bye.